Hello. Today I want to talk to you about a subject I call living RCM. Many of you know RCM, or reliability-centered maintenance. You know that RCM is first and foremost a language, a specialized set of terms and definitions that describe the details and logic of maintenance. It's a knowledge model and a culture that emphasizes a clear line of sight between a preventive maintenance task on one hand and an equipment function that the task is meant to preserve on the other. With that short description of RCM, let's talk about living RCM. Living RCM continues on where the initial RCM process stops. Living RCM addresses two critical problems left unresolved upon completing an initial RCM analysis. Things change. An initial RCM analysis is a snapshot. It is a consensus of best recollections and knowledge of subject matter experts at a fixed point in time. Once the initial RCM analysis is completed, the results are frozen in a maintenance plan, which is then managed within the Enterprise Asset Management, or EAM, system. The problem is that maintenance is a dynamic environment.
New experiences
are encountered daily by maintenance personnel. The RCM analysis, though, is seldom, if ever, revisited. Living RCM continuously updates the initial RCM analysis and its resulting maintenance plan. That's the first problem. The second problem is equally incapacitating. It's the generally poor quality of data transferred day to day via the work order form to the EAM database. That data consists of choices from pick lists. The choices are often ambiguous and error-prone. The problem is that is the only data the maintenance engineer has to work with when conducting reliability analysis. Sure, he's got colorful graphs and great software, but the underlying data itself is inconsistent, inaccurate, incomplete, and therefore unsuitable for reliability analysis. Living RCM solves the problem of unanalyzable data. Data, we all know, is a ubiquitous theme in the marketing of maintenance technology. But what is data, really? What data precisely do we need for purposes of analysis and for making optimal maintenance decisions? Let's try to get our arms around the nature of data insofar as maintenance and reliability are concerned. There are three major categories of data and a number of subcategories. There's what we call age data, also known as event, life, or history data. Then there is condition monitoring data, also known as condition data. And finally, we have business data, which is sometimes called cost data. Age or life data has two important facets: the beginning of a life cycle of some part or grouping of parts, and the ending of that life. For the purposes of reliability analysis, we need an accurate record of the equipment's age at the moment these two events occur. There are two ways that a life can end: by failure or by suspension. Failure is self-explanatory, but what do we mean by a suspension? A suspension is usually a discretionary decision by a maintenance technician, or component in question has not
failed.
It may be worn, but it still has an indefinite amount of life left in it. Nevertheless, we often replace it because it is expedient or worthwhile to do so. In other words, we have suspended the part's life in order to preempt failure. Another word for suspended is censored. Either way, it is vital for the maintenance department, for purposes of subsequent analysis, to distinguish carefully on the work order between instances of failure and instances of suspension. Now let's dissect the concept of failure. There are two types of failure: potential failure and functional failure. They are both failures. The difference is that in the case of potential failure, we have managed, by luck, or thanks to our predictive maintenance strategy, to avoid the direst consequences of that failure. There's also a third kind of age data event. It is known as a non-rejuvenating event. I'll explain what that is in a few moments. The second major type of data is condition data. We classify condition data into two subtypes: measurements and inspections, and process data. Measurements and inspections are conducted specifically for the purpose of predictive maintenance. Process data, on the other hand, is recorded directly within the control platform. Process data can be classified for purposes of maintenance into two types: external variables and internal variables. More on this in a moment. The third main category of data is business data, which is also known as cost data. Cost data has two aspects: the cost of a failure, which we represent by the symbol C subscript F, and the cost of preventing or mitigating the consequences of that failure, which we can call C sub P. The P designates a planned or preventive activity. I should point out that these costs are average costs. They are available from the EAM, or often they are ballpark approximations estimated from experience. We can use these estimates because their absolute values are not needed for analysis and modeling calculations, only their relative values. And there you have it, the nature of physical asset management data. In the third video of this series, I'll show you how to convert age, condition, and business data into practical, verifiable decisions. There are a couple of points I need to go back to before ending this video. The first is an explanation of the term non-rejuvenating event I mentioned earlier as the third type of age data. A non-rejuvenating event is a maintenance action that seemingly improves our condition data but does not actually restore any life to the equipment. Let me show you what I mean. Assume you are monitoring the condition of an engine by recording the parts per million of iron dissolved in the lube oil. A, B, and C are three oil analysis readings. The graph might lead an analyst or an algorithm to believe that somehow the equipment's condition improved at the time of oil sample C. That is what you'll think until you're told that an oil change occurred at time D. So the true trajectory of the line graph would look like this, dropping to 0 at D. Whatever model we use to track the condition of our equipment should not be misled into thinking that the equipment health has inexplicably improved. Instead, our decision process should account for the oil change, which we call a non-rejuvenating event. Other examples of non-rejuvenating events that may impact condition data are alignment, balancing, adjustment, calibration. If those activities will impact the condition data used for predictive decisions, they should be accounted for in the model. The last point I'll discuss before ending this video is the distinction between an external and internal condition variable. Internal variables are predictive indicators that monitor the effects of a failure that has already initiated, and the failure process is underway. External variables, on the other hand, monitor abnormal stresses on a system that may eventually and predictably provoke a failure that has not yet initiated. Maintenance departments tend to focus on internal variables, output from techniques such as vibration, motor current, and oil debris analysis. External variables, however, may provide reliable predictions before a failure process has even initiated. Both internal and external variables should be considered when designing a condition-based maintenance program. Well, that's what I wanted to cover in this video. Now that you understand the nature of maintenance data, you may proceed, at your leisure, to the next video. In that video, I demonstrate how to use living RCM tools to ensure that your data meets the high quality standard needed to perform reliability analysis. The final video of this trilogy demonstrates how you can convert your analysis grade data into verifiable maintenance decisions. Thank you.